Okay, good morning everyone again. Uh, Today we are going to continue talking about ray tracing. We'll finish the geometry part of the slides, which the only thing that is left is how we do ray triangle intersection. So in this introductory ray tracing algorithm, we'll just be considering two primitive types of objects, the spheres and triangles. So as we generate our rays that pass through the center of a pixel, we are going to intersect this ray in our scene with the primitive type of objects, triangles and spheres. And triangles can be used to model, as we've seen, as triangular meshes. We can use the triangles to represent many complicated objects with thousands of triangles. Okay, so this is we'll be able to model scenes which are very complex. Just actually, the triangle may be your only primitive object. You don't need the sphere. You can actually model a sphere by using triangles. There are, for example, in OpenGL, there is no code for drawing a sphere. There is no draw sphere call. So you actually need to have your own sphere by subdividing. For example, you may start, there are different approaches. One approach is by starting from a cube and subdividing iteratively, recursively each of those sides until the more triangles you have, the more your model is going to resemble a sphere. Okay, so for example, with just 100 triangles, actually you can get something very close to a sphere. So it doesn't need to be thousands, depending on how much smoothness you're looking for. But yeah, triangles, even triangles being the only primitive object types, we will be able to model very complicated scenes. Okay, so let's go ahead and start. By the way, before we start, do you have any questions about the assignment or about the ray tracing algorithm so far? I shared with you the code, the version 2 version, in which we have to do this check where in color computation. Yes, we will learn to do shading today to do the homework. So you can actually.
Where did you share these codes?
Excuse me?
Where did you share these codes?
I shared this code on OptiClass.
Like in the section part or all sections?
All sections part.
Oh, okay.
In all sections, let me
Thank
see.
you.
Let me check if you don't see it. Let me check quickly. Oh, by the way, let me first log into my Google account so that all my passwords are here. So that's the bad thing about having your passwords in one place. All right. So here under all sections, here ray tracer version 2. Last week it was November 1st, November 7th week. Yeah, so this is ray tracer version 2. It is yeah, actually. Oh, this one is the one with the bug. We still have the bug, and in announcements, I made an announcement about how to resolve that bug. So this ray tracer output in the announcements on OptiClass, you should have received an email about this. So in order to correct that strange bug, we need to insert this code. We need to check the dot product. So this is actually, we started learning about. Yeah. You can also, I can allow people to, where are the more options? Enable apps participants. Where was that? Allow annotate. Oh, no, actually it was in Zoom. So you should be able to annotate if you want to show something. But here in this one, if you add this code to the buggy version, if you correct it, which means that the diffuse calculation, the dot product between the light vector and the normal vector on the surface, which we use to compute our diffuse shading, should be a positive number because there are no negative colors. If the light is behind the surface, it shouldn't be visible there at all. But that was the reason of that was the this absence of this check was the one causing the error. So we check whether the dot product is positive, meaning that the light ray really see the surface point. Only in that case we add the color information, otherwise the color is black. And the light was the first version, the light was at the top of the scene. So as you can see, the bottoms of the sphere look dark. And the reason is that we only have the diffuse color. The purpose of we are going to see in shading, there is another component which is called the ambient light. The purpose of the ambient light component is to model reflections coming of other objects in the scene. Although there are no other objects in the scene other than these, but in real life, light actually, there is some ambient light in the environment, which are coming off the surfaces of all the objects. I mean, even if this point does not directly see the light, light rays that are bouncing off other objects around it is going to help us see the bottom of the sphere. So that's the ambient component, which means that we don't actually assign 0 to parts where light doesn't reach. We assign some default dark color. For example, it's like dark light reaching there, and depending on what color object is, this will be like a darkish blue here. That will also be represented here on the bottom part of the sphere. So that will not completely be black. That's the purpose of it. And the third component of shading is, oh yeah, that's interesting. I think when it has negative data, that was maybe one of the reasons we had those strange bugs. It looked really, the image we get with the negative colors, or with the negative dot product, we may have also some probably it produced some negative colors there. But how ppm treated that's probably it has some undefined behavior, or it has some defined behavior which we don't understand completely. I don't know whether it treats it modular or so, but that was the reason we had these strange looking effect on the ppm. So if you in the ppm, you should have all positive colors to get something expected. It was really strange. I mean, it was just like the refraction of light through a lens. We get these strange greenish colors on those. The lines look really strange. So I think it was because of those. Maybe it may be the case that the negative values may be ignored, and then the next positive integer is read from the file, which may cause those strange shifting of the columns, or I don't know how it behaves, but my guess would be it may be ignoring those negative values. Or another thing, your guess is also it makes sense. It may be the case that it treats it as a modular, some modular number, and converts it to some. It may treat it as an overflown integer and treats it as a positive number. I'm not sure about that, but we shouldn't have negative values in a ppm file. So, instead of adding ambient component to this code directly, what I did was, okay, I want to see these spheres brighter. One way to do that is just like, for example, if you go into a dark environment, if you have the flashlight just in your gaze, or if, for example, police officers or soldiers, when they move into a dark house, they have their flashlights with them, and the flashlight actually follows their gaze. So one idea to eliminate the spheres was to put the light source directly in the eye. Okay, so when we did that, the spheres actually, all the points we see with our eye, actually the light rays also reach those parts, but it's not completely the brightest color because of the surface normal. Even if we have our light source directly at the center at the eye position, the surface normals on the sphere make different surface points be illuminated at different amount. So these parts, as you can see, are darker. And even with the simple model, I mean, with just simple mathematics of vector dot product, we are able to get some three-dimensional looking spheres in our scene. Okay, so this is really a simple mathematics can help you achieve nice shading and these different things. And another thing in that Leonardo da Vinci biography was that, I mean, he also observed a lot of these shading effects, how different parts of objects are shaded differently, and he has these sketchbook in which he tried different very nice looking shaded objects, surfaces, and he did all by shading himself. So in Turkish, I think it's called tarama. What artists use this. I mean, this is the Turkish of this shading that we are doing, which is tarama, by using a single colored pen, having these effects of lower intensity colors on the surface of objects. Okay, so this is actually the shading part of the first part of the shading part of the ray tracing. We started talking about that, but let me quickly, I'm not going to add more to this code. Oh, you can email me if you have any interesting other bugs and effects in your source code. You can just email me your output and your code along with it. If you have questions, feel free to ask your questions by email. Okay, so you can always send me an email if you have questions or other stuff about when you're working on it. And I suggest you start working on the ray tracing code immediately, because as we are learning these things now, just like we wrote this code, just like we have written this code in class, you should start working on your assignment and build step by step. So the ray tracing code actually is something that is iterative. First you do the ray generation part. Oh, by the way, you can reuse parts of this code we did in class that I shared onto class. So that is allowed in the assignment. You will be able to, if you want, for example, the write ppm part or generate rate, for example, it will be okay if you just get this generate rate function as it is. But as last week, to your source code, you can you have multiple source files? I think I haven't read the homework specifications completely, but if it asks for you to have a make file along with your code, then you can have multiple files, obviously. But if it specifically says that you have to write all your code in a single source file, you should do so. But if it's not stated like that, you're free to, if in the specifications it's not specified directly that you have to provide a single source file, you're free to use multiple source files, as long as you provide a make file along with those. So the way you would add new files is that you would just compile them separately as object files and then link them in your make file at the end. Okay, so, and you can also directly copy and paste these parts if you want these functions. But what I was going to say was, as one of your friends suggested last week, since this is really not an object-oriented way of design, all these rays, colors, we have just those strokes, it would be good to have them as classes. It will be a better design, and you will be able to code more efficiently, effectively, if you do that. So you can get some part of the code, but port it to your design as you fit. Okay, so you're free to use parts of this code. But I'm not going to continue adding more to this code. It was just, we just have seen this output now. And you can try, for example, I can show you something, just one thing more, not adding something to the code, but for example, if we change the scene and make, for example, have the camera to move away from the spheres. For example, it's right now at 20. What if I move the camera to 5 minus to 30? Actually, it was at 50, right? So something I did, actually, I changed this scene, make the camera move a little bit down, I think. So let's try, let's see how it looks like if I move it back. Yeah, they're going to be smaller. And for example, the distortion effect you see on the red sphere is going to get reduced because the distortion, the perspective effect is more pronounced when objects are closer to you. The difference between their closest surface and farthest surface becomes more drastic because it's like 1 over z type of 1 over the perspective, the size of objects are inversely proportional to their distances from us. So that's why as they go far away, so the difference between their closest surface and farthest surface is not going to be that large. So it was here, ray tracer. This is version 2 that I had. So let me try this one. If this is the buggy one. By the way, I changed the code. Let me see. Yeah, I changed the code so that now this convert works. I think the problem was since this is not, I don't know whether maybe the system call is like running multi-threaded without waiting for this to finish. It probably goes to the next system call. Maybe it just gives this as a process to the system and just executes the next one. And the next one was deleting output ppm, and that was causing the error. So if you don't delete output ppm and just make this convert function call from your write ppm, output png is nicely generated. So this is output png. Yeah, as you can see, I changed the colors a bit too. They are now smaller. They are and they're a little bit lighter because their colors, as you can see, this is not RGB 0.3, 0.3, 1.0. It's this is red. Red is sorry. This is the blue one, but it contains some red and green. 0.3. So let me also open this scene.txt in Notepad++. So therefore, it has this pastel color with some red and green too. And also, this is the red sphere. I did the same thing. If you just add green and blue components, it gets closer to white. And for example, what will happen if it's purely white? So let's make this blue sphere a purely white sphere to see the shading effect maybe more clearly. So let me just close this, run it again. Okay, since it's in my scene file, I don't need to recompile it. Now it should be here, output.png. So this is the pure white one. As you can see, it's not pure white, it's grayish parts of it. Maybe this part is more close to white, but now this is like, you can see the shading effect, how diffuse color reduces as the dot product of the normal vector of the surface with the light vector gets closer to 90 degrees. Okay, so you can try different changes. You can change the scene file to see different effects, change the colors, and the next thing you will do in the assignment, the next thing you should do is to add triangle intersection. Just like we have this intersect sphere function. You just add intersect triangle function by just referring to these slides. I'm going to talk about two methods to intersect triangles with rays, and you can choose any of them. I think the one with the barycentric coordinates is a faster implementation than the other one. So if you want your ray tracer to be fast, you should just implement that one, and the formulas are already on the slides. All you need to do is again just convert them to, and if you understand, you can do it on your own too. But yeah, I mean, even if you don't understand the mathematics completely, what I'm saying is that it will not be difficult to convert what you have, the solution on the slide, to C code. After you have intersect triangles, you can try, for example, to visualize triangular meshes. And here's how we should modify our color file, right? How are we computing the color of the scene? So this was intersect sphere. So there should be another function, intersect triangle. And here in our compute color function, we should try to intersect our ray with all the spheres, and we should try to intersect our ray. We should have another for loop that goes over all the triangles in the scene. And another thing with spheres and triangles is that, for example, okay, on a sphere, the normal vector along the surface changes depending on the point of intersection. But for a triangle's normal, a three-dimensional triangle with XYZ coordinates P1, P2, P3, a triangle, it's a planar surface, so it will have a fixed normal vector. Okay, so it makes sense after you read those triangles. It's it's a good idea to just compute this normal vector and store it just as a material property. And it's not a material property, it's a geometric property, but store it as a property of the triangle, because this normal vector is going to be constant throughout the surface of the triangle. Okay, a triangle looks always to the same side. A triangle, unless you rotate it, you move it, the normal vector is going to be fixed. So given the three corners, three vertices of a triangle, you can compute the normal vector by, for example, P2 minus P1 cross product P3 minus P1. So this formula, just some vector algebra, will give you the normal vector. And if you normalize this with this length, if you get this vector and take this normal vector, it will be, if it's a make it unit length vector, it will be the normal vector of this triangle. Okay? So yeah, if you pre-compute it for the triangles, this is how you should compute. When you're computing the color in your scene, you should also know whether this, for example, when we're computing the diffuse color, what we have here, the normal vector, for example, this code we have written here is true, it's correct for a sphere, but it will be incorrect for a triangle, because the triangle, it's incorrect for a sphere, because spheres do not have centers. So depending on what type of object hits your ray closest, you should have two different pieces of code here which has the normal. Why we cannot compute the color with light for spheres? A good question. Actually, let's think about it. You didn't miss the point. It's a good question, but why we cannot compute the color for spheres? Let me ask you this: how many points you're going to pre-compute the color on the sphere? How many points does your sphere have on its surface? Yeah, yeah, you got the question. It's infinitely so, but our rays are not infinite. So we only do the computation when our ray hits a point on the sphere, and exactly. So what we do is, actually, this is ray. So since we have to do it for all of our rays, that's exactly what we do. We have a ray that we pass through a pixel center, and when that ray hits the sphere, we compute the color at that point on the sphere only. Okay, so this is what we can do. Well, with the triangles, actually, this is a very good point. With triangles, for example, one thing OpenGL does, and it does it very efficiently, is that this is not we do in ray tracing. In ray tracing, we're also, again, when our ray hits a particular point inside a triangle, we would compute the color, we would make the color computation for that specific point that we hit on the surface. But what if we pre-compute the colors at the vertices, and when we hit a point inside a triangle, we interpolate, instead of recomputing the color from scratch for this point, we interpolate the color that were computed for the triangle vertices. And this is what we will do. We will use a different color shading model in which we will not, this will make it a lot more efficient. Instead of having to do all those normal vector calculations, color computations per pixel, we would just, for example, maybe compute the colors at the vertices first, then do interpolation by linear interpolation, which means that, I mean, it's a two-dimensional surface. When we are doing interpolation, we need to interpolate along, for example, vertical lines and then along horizontal lines. So we have to do something bilinearly in two dimensions, basically. So this is what it means. Linear interpolation, but you do it twice because you're in two dimensions. A triangle surface is two-dimensional, but those are all really good points. The reason why we don't pre-compute the colors is that our ray may hit one of the infinitely many points on the mathematical definition of a sphere. But what we are seeing here on the sphere, where is my PNG image? When we look at this, the number of things, when you zoom enough, you're going to see that actually it's not, we have our pixels. So whatever the resolution of our image is, we actually send that many pixels and we compute the, but it looks really smooth because our resolution is really large. There were thousands of pixels on an image. Yeah, rays intersect with objects, and yeah, we are only going to use rays to intersect with objects. Yeah, it's 2 million or 2 million pixels intersect. So that's why actually ray tracing is slow. But you can also imagine that this is what in parallel computing, if you've taken parallel computing class, there's a term that says embarrassingly parallel. I mean, I've heard this term in some article. So embarrassingly parallel means that it's trivial to parallelize this, because if you consider your for loop, it's for every pixel we run the whole tracing algorithm for every ray separately. We don't actually use the coherence between two pixels next to each other. We don't do any interpolation. Each pixel we compute its color separately compared to the other pixels, which makes it that if you share your scene data with your threads, you can have a multi-threaded program in which each thread may be responsible from separate rays. So this is really how it can be really parallelized easily, ray tracing. So let's go ahead and now talk about how we can do ray triangle intersection. I will first start with a slow but more intuitive method. Let me use my GIMP. Yeah, right here. It was already open. So let me get a new fresh whiteboard. So here's our question. We have a ray. It has an equation. Okay, E plus dt. It starts with some E location. It goes in the direction D, and this is our ray equation. Now we have a three-dimensional triangle, and our goal is to find the intersection. I mean, if I say three-dimensional triangle, a triangle in 3D space. Actually, a triangle is a two-dimensional surface. Okay, so a two-dimensional object, a triangle, and any point on its surface actually can be parameterized. We can parameterize triangle by two values, just like a geodesic surface where you have latitude, longitude. Your unique position on a triangle could be identified by two parameters. There's a parametric equation, parametric, just like parametric line equation, there's a parametric triangle equation, and it actually goes like this. Any point, actually it's about the other method, but since I've started about parametric triangle equation, let me also just give you this as a side note, and we are going to be using this solution as the faster solution, which is this. Given 3 points of the 3 corners of a triangle, a triangle equation can be something like this. A point on a triangle. Actually, I'm going to write 3 parameters here first, but one of the parameters is dependent on the other parameters, so actually there are 2 degrees of freedom. It's nothing but a weighted average of its 3 corners. So that's an interesting way to look at a triangle, but it's actually the triangle, any point on the surface is a weighted average of its corners. So if these w's can be any numbers, actually we will be getting points that are outside the triangle. So we have some restrictions on these weights. When I say weighted average, usually weights should be between 0 and 1. If you're doing a weighted average of things, they should be between 0 and 1. And another important thing is that they should add up to 1. Okay, so if these W, W1, W2, W3 are real numbers between 0 and 1, they're non-negative. And if they're all between 0 and 1, and if they sum up to 1, that gives you a valid triangle equation. The fact, this fact that their sum is equal to 1 actually reduces our degree of freedom by 1, which means that instead of this parameter W3 here, all I need to do is write 1 minus W1 minus W2. As you can see, it's a 2-parameter surface. So this weighted average thing is one thing that we can have to represent it. And these are actually this W1, W2, W3. We are going to replace them with some Greek letters. We are going to name them alpha, beta, and gamma. Okay, and maybe by just using alpha, beta, gamma. These alpha, beta, gamma values, these weights, are called the barycentric coordinates of a point. So this is barycentric coordinate representation of a triangle. And for example, they will be proportional. For example, if we have a point here, these barycentric coordinates could be found by looking at the areas of these subtriangles. For example, when the area 1 is 0, the ratio, I think we can say that area 1, the ratio of area 1 divided by the whole area is, for example, if it may be the weight of P2. Okay, so whatever the weight of P2, for example, I can say this is W2 because when this area is 0, you're basically taking a weighted average of P1 and P3 if W2 is 0, which means that you're currently on this line. If just think about P1 plus some weighted average of P1 and P3, it will just be like a line equation and you will be on this edge, which means that this area, as you move this point inside the triangle, these areas are going to change. And if A1 is 0, for example, you can see that the weight of P2 is going to be 0. So that's one way to represent triangle. But yes.
Is that P equal is between 0 and 1? So this sum also equals to 0 and 1. I mean, it's between 0 and 1.
Yeah, it's between 0 and 1, and all these W1, W2, W3, they all have to be between 0 and 1, and their summation have to be equal to
1. Okay. No, what about T?
There's no T here. These are pluses. P?
Yes.
Oh, this is not multiplication. This is a function.
I see. No, I mean that. What is the like range of this P? And
Oh, the
I
range of
couldn't
P.
actually get the idea
Okay.
why this is an equation.
Yes,
Like,
exactly. This is like a parametric equation. It will give us a point, which will the range of P are the points within the triangle's inside area. Okay, so as you change W1, W2, W3 between 0, 1, all these numbers, P is going to give you, I mean, if you change W1, W2, W3 to all possible numbers they can take between 0 and 1 satisfying this equation, it will give you all the infinitely many points within this triangle. So this parametric triangle equation generates the points inside the triangle. Okay, it's ranges, so its ranges not between 0 and 1 or whatever these coordinates are. So this is P is a three-dimensional point, just like P1, P2, P3. So P1 is a three-dimensional point. We multiply it with a scalar. We add it with
yes,
another
I see.
scale three-dimensional point. So these are like addition of three-dimensional points, but just scale.
We try to somehow show that this ray intersect the surface.
Oh, right now we have two separate equations. So we have one ray equation. We didn't intersect. We haven't done the intersection yet. I just talked about.
I see. Like I just said that our aim is that.
Exactly. Our aim is that. So we have one triangle equation that is like this. Actually, let me. Since I talked about this pericentric coordinate, we can actually try to do the intersection. Let's see. What will happen is that in intersection, our goal will be at this intersection point. Imagine there is an intersection point P. Which means that at this P, the ray equation with E plus dt is equal to the triangle equation. So I will have this E plus dt equals to alpha P1 plus beta P2 plus 1 minus alpha minus beta P3. So this is the equation that I will be using for the intersection test. I equate, this is the triangle equation I have on the right. So this part is clear, right? I mean, this is the triangle equation. Triangle is identified by its three vertices. And any point on the triangle satisfies this equation, with provided that alpha, beta is between 0, 1. It's an element of this interval. And also their summation is less than 1. We can say that alpha plus beta is less than 1, less than or equal to 1. And that's it, I think. Because if this will be their summation is less than 1, it also covers this W3 as well. Okay, so with these two constraints, this is the triangle equation, this is my ray equation, so this is the equation to find the intersection point of a ray with a triangle. Now, let's look at this equation. How many unknowns I have in this equation? What are the unknowns? 3. T,
yes,
alpha,
beta, T.
and beta. Alpha, beta, and T. So 3 unknowns, 1 equation. Can I solve this equation? 3 unknowns, 1 equation? Or am I saying something wrong? Is it really 1 equation? No, exactly. It's actually 3 equations too, right? Because these are vectors. So I can write actually 3 equations for x. For example, E is a vector, D is a vector, P1, P2, P3 is a vector. I actually have 3 equations and 3 unknowns. So this solution requires to solve a linear system of equation with 3 unknowns, 3 equations, and my equations are this: Ex plus dxt equals P alpha P1x plus beta P2x plus 1 minus alpha minus beta P3x. So that's one equation. I will write the same thing for EY, the y coordinates, so they're independent. So since x and y coordinates, they're in orthogonal space, the x coordinates, y coordinates, they're independent from each other. These are really independent different equations. It may turn out that for example, your ray may not intersect the triangle at all. There are two ways for non-intersection. First of all, your ray may be parallel to the triangle. In that case, these equations they're going to cancel out. In this first point, the dual phase, we don't consider the triangles as dual phase at this point. The dual phase is going to come into picture when we consider the normal vectors of the triangles, because a triangle will have two normal vectors. For example, if this is a triangle that you see here, it will have a normal that is facing you, and it will have a normal facing. At this point, at the intersection, we are not considering triangles faces their direction. Okay, so actually this equation, this parametric line equation, are just going to give the points. It will give you a point on the sphere. We will not consider whether it's that the back is facing front or back. But this front and back idea will come into picture when we are computing the colors, because there are two normals of a triangle. One is facing this way, the other is facing the other way. Which one is actually the normal of the triangle? So it will come into picture at that point. But as you can see, three equations, three unknowns, t, alpha, beta. I'm not going to go into details of, there are different methods. For example, you can invert the 3x3 matrix. So it will be something like this. Some coefficient matrix multiplied, actually some matrix multiplied by some other column matrix is going to be equal to another column matrix. It will be something like this. So I can actually write that. You can write your unknowns here. So alpha, beta, gamma, alpha, beta, and t is going to be somewhere here. And whatever the right-hand side equation, it will be the known things here. What you can do is you can multiply both sides with the inverse of this 3x3 matrix. If you multiply these constants, coefficients, with the inverse of that 3x3 matrix, it will give you alpha, beta, and t. So these are from mathematics or linear algebra, how you can solve linear system of equations. But it's given directly on our slides. Let's take a look at that. So this was all about barycentric coordinates. So yeah, this is the matrix that we have. So this is the A matrix, the knowns. By the way, this AX, BX, CX, these are ABC are the three corners of our triangles. Okay, D is the direction vector of our ray. O is the origin of our ray. So if you work out the equations, the matrices come to this, and all you need to do is find the inverse of this to solve for alpha, beta, and this one alpha is taken out. So it's the two parameters you have is beta and gamma as shown on the slide, but it really doesn't matter. You shouldn't think that, okay, we have learned this on the whiteboard, we have seen something else, there is no alpha here. It's just actually the idea is the same. Whatever you put, you could have taken beta out as the non-free parameter and just make up the equations by using just alpha and gamma. It really doesn't matter. The fact is that in barycentric coordinates, two of those alpha, beta, gamma variables are this. Oh yeah, that's actually that's the second method I will talk about. Yeah, because with this triangle equation, this 3x3 equation, this taking the inverse may seem inefficient, but actually when you take the inverse, you can also use the Cramer's rule. To solve this 3x3 equation, you can use the determinant of this 3x3 matrix and solve that. It looks really inefficient, and mathematically driving these equations seem to take longer, but actually the determinant of this matrix is given by this, and yeah, what you need to do is you need to implement this part. Okay, so if this is the determinant of a 3 by 3 matrix, you just apply this to these values here. It may seem a lot longer in code, but it will just be multiplications, and some of these values you have here, some of these determinants, for example, the determinant of A is used only once. You compute four different determinants, 4 equations, and alpha, this beta, gamma, and t will be computed much more efficiently than using other vector operations, the alternative method. Actually, the other alternative method, which is the intuitive one that you just mentioned, if we generate the plane equation for the triangle and then we intersect the plane equation with the triangle, it will just be an equation with one unknown t. We are going to see that. And it's actually much more intuitive to do the intersection, but those vector algebraic things that you do to compute the normal, for example, you have to, in order to get the plane equation, you have to first compute the cross products and then do the plane equation with the ray equation intersection, and then check whether the final thing is your ray may intersect the plane of the triangle, but it doesn't mean that it intersects with the triangle. So I was just mentioning 2 cases where our ray doesn't intersect the triangle, right? So you may have a ray, you may have a triangle. There are 2 ways your ray doesn't intersect the triangle. One is your ray may be parallel. So it may be the case that you have a triangle here like this, and your ray actually may be parallel to your triangle, and intersection will occur at the infinity, so they will never intersect. That's one way. The other thing is that your ray may just pass through your triangle from its side. It doesn't penetrate the triangle, but it goes through the plane of the triangle in some other point. So therefore, when you do normal, when you use the plane of the triangle and try to intersect your ray with the plane, in addition to finding the intersection point, you have to check this point triangle inside outside test. You need to explicitly check whether that point you have found on the ray plane intersection point, is it inside the triangle or outside the triangle? Okay, exactly. This is exactly what you have written. That's the second method. When you implement it, it's a little bit slower than this one. So this is the, I mean, converting this to C is not so difficult. So you have to write this. If you have a matrix like this, oh no, it's not an interruption actually. Thank you. Thanks a lot for the question. Because it was the other method that I would discuss anyway. So it was good that you brought it out. And here, if you just write, you just need to have a function that says determinant 3 by 3, for example. You may write a function named determinant, for example, void, it's not going to be void, it's going to return a float value, determinant 3 by 3. It gets a float matrix, okay, like this. You can get your matrix, and then all you need to do is write whatever you have. Here, this single equation will just be, for example, M00, these are multiplied, subtracted by this. Just convert this to a single C expression, and you have your determinant. And after that, just use the determinant function to compute these 3 determinants. Form these matrices, form 4 matrices with these values. All of the values you have here are known things from your ray and triangle. These are your triangles, corners, your ray origin, and your ray's direction. All of the things inside these matrices are known. Okay, and by the way, this A matrix is this one. Okay, it's also something that we know. Okay, So, and you just define the determinant, compute the determinant, call the determinant function 4 times, and compute these things. After you compute that, another thing is that this beta, you may solve for beta, gamma, and t, but if beta is greater than 1 or a negative number, the same for gamma, it means that your ray doesn't intersect the triangle. So you need to check for the condition where alpha and beta, in this case beta and gamma, if you're using these equations, they are between 0 and 1, and their summation is less than 1. Okay, you should have these checks to ensure that your ray intersect the triangle. If that's the case, you just return t from your function, and that t value, if it's negative, for example, the ray triangle intersection is behind your back, so again, you ignore that. Or even if it's between 0 and 1, it may be your triangle is inside your camera, whether you see it or not. I mean, we have discussed this last time. Actually, being able to see things that have t values greater than 0 is biologically or physically more correct. Than I mean, we can consider that our camera is actually starting at just beyond our eye point, so checking whether t is greater than 0 is also going to make sense. But in the assignment, don't worry about this because all of your objects are going to be strictly in front of the image window. They are going to be in front of the image plane. If there are objects that are behind, you don't need to visualize them, or you will not need to worry about cases where objects are inside the camera, between the eye and the image window. So that's this concludes the geometry part. So there is more discussion. If you go on the slides quickly, for example, we have triangles. We talked ray plane intersection. That's the second method. One thing we can do is we can form the plane equation given 3 corners of a triangle, P1, P2, P3. We can form the plane equation in which this triangle is on. Yeah, actually, we can check if t is greater than 1 to determine that there's an object in front of our image window, and we see that. So checking t is greater than 1 can be done in the compute color function after that gets the intersection point t. So yeah, this should also be checked, because when t is negative, you shouldn't compute color for objects that are behind you. Okay, so in this, how do you compute the plane equation if the 3 points of a triangle are given to you? It's simply like this. By the way, any plane equation, so this is the plane equation, this is the general plane equation in 3 dimensions. CZ plus D is equal to 0. So one interesting thing about planes is that this vector ABC is actually, it actually gives you the normal vector of the plane. So if you have a plane that this triangle is lying on, this normal vector is also going to be the same as the normal vector of the triangle. So which means that this, you can actually, by doing this P2 minus P1 cross product, P3 minus P1, you can get this normal vector. Since this normal vector is also the normal vector of the plane that this triangle is on, it directly gives you, the cross product directly gives you what ABC is. Okay, so you find your ABC in this equation with just one cross product. And the only unknown thing in your plane equation is D. How can you find D? Because there are infinitely many planes that have this normal. If you shift your plane up and down along this normal vector, there will be infinitely many planes. So there's another one thing that fixes this plane to this particular point that has your triangle on. All we can just plug in any point to this plane equation. We have only one unknown, D, to fix this plane equation, and you can just plug in P1, P2, or P3, any of them, any of those 3 points, plug one of them into this equation as x, y, z's. Since you know ABC, this is P1x, P1y, P1z, and then the only unknown in that equation will be D. solve for D, you get your D. So after that, your plane equation is complete. After you have your plane equation, plug in your ray equation for these. So ABC, after you know ABCDs, plug in your ray equation into these XYZs. You will have only one unknown, T. So it's one equation, one unknown again. So it looks like it's simpler than the other three unknowns, three equation thing, but you're solving iterative multiple steps. You first find a normal vector, then you solve another equation, ray plane intersection by plugging in your ray into this equation. You find a single T. After you find that T, you plug this T in your ray equation, you find the intersection point P, and then check whether this P, it may be outside this. You check whether this P is inside this triangle. How do you do that? Again, the point inside-outside test in triangles can be done like this with cross products. We check whether this P is to the left of this edge, and to the left of this edge, and to the left of this edge. If a point is to the left of all of the edges when we traverse the triangle counterclockwise, okay, when you're going along the triangle border counterclockwise and you're traversing the edges of your triangle counterclockwise, a point that is inside the triangle should be to the left of these edges. And how can we check whether a point is to the left of a line? By, again, cross product. So we need to do 3 more cross products to check the cross product of, for example, if the cross product of P2 minus P1, this cross product P minus P1, if the Z value of this cross product is greater than, or it's not the Z value actually. Oh yeah, so this plane is an arbitrary plane. It's not parallel to the xy plane or the xz plane, anything. So they will have arbitrary values. So what we need to check is that we cannot directly check the sign of this cross product. But this cross product is going to, we can check whether it's equal to this normal vector we have computed earlier. Okay, so that's another thing. So we have computed, if it's in the same direction, we have already computed a normal vector in one direction. If this cross product is in the same direction, it may be multiplied with some scalar, because this cross product here is also going to give the area of the triangle, so it will not be normalized. But if you just check whether it's the same direction with your normal vector, it means it's to the left. Yeah, we can pre-compute lots of these equations for each triangle. You're not wrong. These triangles are fixed. You don't need to do these ray triangle intersection tests. During ray triangle intersection tests, lots of things like this cannot be pre-computed, but the normal vector is pre-computed. So which means that the plane equation of the triangles may be pre-computed. So the first step of this type of triangle intersection method can be pre-computed and stored. So you may have your normal plane equations stored alongside with your triangles. That will speed up. Exactly. So it's a really good idea to see which parts of this equation I can pre-compute. What does it change? For example, if you look at these matrices here, for example, you cannot pre-compute these parts because there's something that depends on your ray, this dx part. So this part you cannot pre-compute, or in this type of equation, the ray plane intersection, again, you cannot pre-compute because your rays change every pixel. But your plane equation for a triangle is fixed. So pre-compute that first step. That's a good idea. It will speed it up. That's a really good idea. And yeah, this ray plane equation, you can form it like that with triangle. So we did this earlier, and this is lengthy but simple method. Simple in terms of it's like I call intuitive. So form the plane normal vector with cross product, then find the plane equation. This is the implicit plane equation. It's different from our ax plus by plus cz type of thing, but it's basically the same equation. So the plane equation is found by having the forming this. You have your normal vector, any point on the plane, if you take the normal product, take the dot product of that, any point on the triangle, minus A or minus B or minus C. This A could be any one of the 3 points on your triangle. So if you form the vector on the plane, its dot product with the normal vector should be 0. And this actually gives you the same equation that we know, ax plus by plus c. It's the same, just represented differently here. And then if our p prime or our prime or p here is on the same side of the edges, it's inside. If one of it's out, not the same side on the in one of the edges, it's outside. So we have to check this inside-outside test here. Yeah, even with pre-computations, it may take some time, especially this inside-outside test. I think these cross products. I mean, we have practically tested this. So I had this method implemented in my ray tracer. Ozoja had implemented the other version, and this one we have tried both of them. I mean, the other one is a little bit faster. Yeah, and this is that other one, the barycentric coordinates. I mentioned about this, the areas, how this barycentric coordinate equation gives any point on the sphere. And you can also intuitively visualize these barycentric coordinates to be like this, but that's just another way of looking at that. For example, I view the barycentric coordinates as weighted averages of 3 corners. And you can actually view them as coordinates along this plane, alpha, beta, gamma plane. Okay, so these are just things about the barycentric coordinates. I'm skipping those, we have already mentioned. And we have also done 3 equations, 3 unknowns thing, the other method. So this is done. And right now our ray tracing algorithm is like this. So yeah, these are the equations. So whatever our minimum t that we're looking, so we check whether our t is between some bounds. Why do we have a t max? In some computer graphics applications, we may just limit our view to the some largest distance that we can see. Okay, so that's sometimes this is called the far plane or the farthest distance that you can see, but this may be some very large value that you don't need to check at all. And we check whether they are greater than or equal to 0 and their sum is less than 1. And that's it. That's triangle intersection. And the basic ray tracing algorithm is right now, as in our code, we compute the ray, we do intersection tests with our ray with all of the objects in our scene, all the spheres, all the triangles, and we keep track of the closest object that hits our ray. And we also, after we maintain that object, we maintain whether it's a triangle or a sphere. With that, we compute its surface normal. And the next thing from in the second hour, I'm going to talk about how the color, the shading part. We set the pixel color value computed from that hit point on that surface. Since objects may have infinitely many points on their surfaces, the points that we are actually computing is limited by our resolution, by the number of rays we generate. The more ray you generate, the more smooth or the more detailed colors you're going to be able to see on the surface of the object. So here are some complex models at the end of these slides before we take a 10-minute break. Let me just go quickly through over them. So this one, 700,000 triangles. They also contain some color texture information. This is not pure geometry. I mean, the fact that some parts, these crevices, they are whiter and the other parts are like brownish color. It means that there's some texture applied, texture mapping applied on this body. This one, this Buddha model composed of 9 million triangles and 5.5 million. So there's no texture mapping on this one, for example. This dragon model is pure gray, but it's not only diffuse color. So you see this, if you look at the shading of this, so there's some parts are darker, some parts, there is maybe ambient component here as well, but if you see, there are some shiny spots. It looks, this dragon model looks shiny, and this shininess is going to be modeled by that third component of our shading model. I told you that there are three components: ambient, diffuse, and specular. That specular component is going to be used to model these shiny parts, shininess of objects. So this is 7.5 million triangles, so there are a lot of, just look at this one, 116 million triangles. It's a lot more than the number of pixels we have. So it will sometimes, if you have not an efficient implementation of ray tracing, generating this figure this image may take days. And this one just shows our intersection cost right now. If we have, for example, a 1 megapixel image, 1 million pixels. If we have a scene which is composed of 1 million triangles, we will have to do 1 trillion intersections for those in total. And this is just intersection part. Then computing the color, which we are going to talk about this week, is going to come next. After we find the intersection, we are going to compute the color for our pixels. That's also going to take some computational resources. And but these days we use graphics processor unit, multiple computers. We parallelize this process. And these intersections, they can also be made efficient, more efficient. If we have a hierarchical data structure built over the triangles of our model, we can actually adaptively filter out certain regions of our scene, which will actually reduce that is the most important speed up, not just parallelization. Parallelization is just one way to speed up, but a nice intelligent data structure built up on top of your triangles will reduce the number of triangles that you are intersecting with to some logarithmic complexity. So it's going to be much more efficient this way. These acceleration structures, this is the biggest advancement towards high-speed ray tracing. And we are going to now, in shading, it's not just the three components, diffuse, specular, ambient. We are also going to see methods to generate shadows and reflections. So we are going to see first how to compute the color, ignoring shadows and reflections. And then we are going to see how we can add shadows to our scene. And then how we can add reflections to our scene. And that last part, the reflection part, makes the ray tracing algorithm actually, it gives its name. We'll be tracing the ray through reflection rays to get this nice reflective surfaces. Okay, now let's have a break until 11 a.m., so about 12 minutes. And I will stop recording, but if you have any questions from this geometry part, I will be happy to answer them during the break.